to remind you people what we are discussing. We're discussing the art gallery problem in general, and mixed with the art gallery problem, we have triangulation of simple polygons and coloring. It's kind of a mix-up of everything. We are in the chapter that talks about the art gallery. So far, what we established is that every, if you'll give me a simple polygon without holes, I can pick two vertices that seize each other. It takes a proof why that there are two vertices that seize each other. We can pick another two vertices that seize each other, and the chord between them doesn't cross the first chord. And I'll keep doing this exercise until I cannot add any more chords, any more of these segmented connected vertices. And once I'm done, and if my lines would have been a bit more stable, you'd see a set of triangles. And we figure out exactly how many triangles we are generating in this way. Sorry, people on Zoom. Yeah, I had to update the OBS. People in Zoom, if I'm doing things like not updating the OBS or the slides weren't clear, please let me know in the chat. I do see your chat. So we can triangulate it, and if we are triangulate it, we will, the big problem that we are handling is putting guards so that the whole polygon is seen, every point of the polygon is seen by one of our guards. And our algorithm so far was along the line of let's triangulate it. And I'll show you that I can pick one of the vertices in each polygon, in each triangle. Sorry, I can pick one of the vertices of each triangle, trying to recycle a vertex of triangle multiple times. So basically, if it's a vertex that is shared by many triangles, is probably likely to be picked, such that each one of the triangles is hit. Pick a guard in one of the vertices of each and every triangle, and altogether I will use no more than n/3 many guards. And how did I prove it? I claimed, and of course you need to be very suspicious because I didn't prove it, I claimed that I can color the vertices of the polygon using 3 colors, such that in every triangle I have a representation of each one of the minorities. Each one of the groups will be represented in each one of the triangles. And now the n/3 will get, just because I have n vertices and I am using 3 colors, so one of the 3 colors should have at most n/3 many vertices. But so far you don't know that I can indeed fulfill my colors. That is, maybe once I'll start to color, if I'll pick, here is a way to do it wrongly. Would be, say, if I'll decide that this color is green in the middle, and this will be blue and red, and blue and red, and I'm now in troubles. But which color should I give to this vertex? I cannot color it green, because then this triangle will have 2 greens and no red on it. I cannot color it red, because then this triangle will run into the same issue. And I cannot color it green, because there is already green, and I cannot color it blue. Everybody agrees? If I try to color it blue, this vertex, then this triangle has blue and blue. No, 2 blues, 1 green, but no red. And I promise that every triangle have a vertex of each color, because I want to guarantee that when I pick this color to be my guarding set, somebody sees everything that happens in this triangle. If you have painting on the walls of this room, one of the girls keep watching these paintings. That's why it's called the art gallery. So this was a bad algorithm for coloring the vertices of this polygon. But, oh, by the way, it's not really a polygon, right? Definitely not if it's simple one. There is some hole in the middle that somehow suggests that things can go wrong. Okay, so I need to fulfill my promise about the coloring. And the algorithm is quite cool by itself, and in the homework I ask you of other approaches along the same line, using similar arguments. So, every triangulation of a simple polygon has an ear. An ear will mean a triangle, but two edges of this triangle must be edges of the original polygon. But if you look at this simple polygon, you see several, I already triangulated it. You see a bunch of triangles, but if you think about this triangle, one of its edges is a chord edge, an edge that I added for the triangulation. Another edge is a chord edge of the triangulation, and only one of its edges is edge of the original polygon. Exterior edge, if you will, exterior wall. And here will be a triangle that have two exterior walls, at least two. And it could have three, but then your original polygon is not very interesting. It's just a triangle. But you see that there are a lot of bad triangles out there. And also I want to demonstrate to you that this requirement that my polygon is simple is really necessary, because here is a polygon with a hole in the middle. I triangulated this non-simple polygon, and if you check it out, each one of my triangles have only one exterior wall, or exterior wall over here, and two of its edges are chords of the triangulation. So the requirement of simplicity is important. So the theorem states that every simple polygon must have an ear. Let's see how I'm proving it. So, okay, this font is way too small. I'm looking at the dual graph of the triangulation. I told you already, kind of, without spending too much time, about what is a dual graph of a map. If I have a map, any map at all, triangles, non-triangles, I don't care. It has vertices, it has edges, and it has faces. Let's give the faces name: F1, F2, F3, F4, F5, and F6. And now I want to tell you what is a dual graph. So when I'm creating a graph, I need to tell you what are its vertices. And the dual graph doesn't care exactly where are the vertices geometrically, but inside every face, I will put a vertex of the dual graph. So in F1, I will put a vertex, which for conveniently, I'll call just V1. In F2, I will put V2 somewhere. You'll see in a moment why I'm not very determined where exactly in the face I'm putting this point. It doesn't matter. In F4, I will put V4, V5, and V6. F3 will be V3 and V6. So we are doing vertex of the dual in each face. In each face of the map, I placed a vertex. In the example of the polygon, it will be one vertex in each polygon. That's how I start building the dual graph. Now, what are the edges of the dual graph? So edges of dual connect two neighbor faces. Now look at every two faces that are neighboring. Every two faces of my map that are neighboring. Neighboring means that they must share a border. I think that in one of the slides, Utah and New Mexico don't share a border. They meet at a vertex, but we don't think about them in this definition as neighbors. Here, F1 and F2 are neighbors, so I'll create an edge between them. Between the vertices that I placed as a representative point. F2 and F4 are neighbors. F3 and F2 are neighbors. F5 and F3 are neighbors. Connect the representative vertices. F6 and F3 are neighbors, so connecting them by an edge. And probably forgot somebody. F6 and F1 are not neighbors, don't share an edge. To make it a bit more, you can add the outer face if you want and connect it to all the vertices, all the faces that shared an edge with the outer face, but it will occlude my graph. But you see what is a graph that I created. It has 1, 2, 3, 4, 5 edges, basically for every pair of faces that share an edge of the original map. Now, in this case, it happens to be a tree. Sometimes it will have cycles, and sometimes it defines faces of its own. That's why we called it a dual graph. So it has vertices, it has edges, and sometimes it has faces. Here we just have one face, but I can easily create more interesting examples, and we'll see many more interesting examples when we'll talk about Voronoi triangulation and Voronoi diagram. But anyhow, now you know what is the dual graph. And dual has plenty of cool properties. You take the dual and you ask what is, since it's plane, if I start from a planar graph, then the dual will be planar. Not really surprising that I don't have crossing edges if I just connect them along faces that are neighboring, but still not entirely trivial. What you're getting as a result will be a planar graph. And then you can ask now for the planar graph, what will be its dual? And surprise, surprise, what will be the dual? You're going back to the primal, to where you started. And it has plenty of cute properties that actually will be relevant. Anyhow, now I am creating a dual graph of my simple polygon. What would be the dual graph of my non-simple polygon? It will be a cycle. Basically, I can walk from one triangle to a neighboring triangle, to a neighboring triangle, to a neighboring triangle, and keep on walking and never stop and continue forward. But that's in a polygon that is non-simple. What happened in a polygon which is a simple? What can you tell me about this graph? So I'll show you two proofs. One that does use this notion of dual for the one that likes it, and one that I don't mention dual for the one that will not. How bad is this font? Should I do the editing now? Readable. So let's talk about the dual. I created the dual graph of my polygon. Every triangle, that's my map, has a vertex. Every two triangles that have an edge chord that separates them. It must be a chord, it cannot be an exterior one. A chord of the triangulation that shares between these two triangles. I'll connect the two vertices, these two vertices of the dual graph, I'll connect them by an edge. And since I started from a simple polygon, this graph that I'm creating is a tree. You cannot have a cycle of triangles exactly as opposed to the case that you see in the other example. There is no cycles. It's a tree. What a tree, just to remind you, is any graph that is connected and does not have cycles, cycle-free. If you are used to see trees as this part, something like this, these are formally called rooted tree. And if I'll show you a tree that is not rooted, like the blue one over here, pick any of its vertices, let it hang up, and let gravity pulls everything down, and it will become a tree that has a root. Then it's a rooted tree. Back to our argument. This graph has a leaf. At least one. Every tree has a leaf. If it's a path, it has 2 leaves. So actually, every tree has 2 leaves. Cycles doesn't have leaves. So what does it mean, a leaf in a tree? It means exactly a face, a triangle, that has just one edge that connects it to the rest of the graph, just one diagonal edge, meaning that the other 2 walls are exterior walls, and this is the ear that I was arguing. Okay, that's with dual. Here is another proof where I don't mention the word dual. Pick one of the triangles, whichever you want. Assume that it has an exterior, assume that it has a boundary which is a chord. That is, he has this triangle has another triangle neighboring to it. That is, not all the edges of the first one are exterior walls. I can move from this triangle via a triangulation chord to another triangle. If my next triangle is an ear, then I can enter into it via this chord, via this diagonal, but I cannot exit. That's what makes it an ear, that you can enter via one chord, but you cannot exit via a different chord. In this case, this triangle, it has 2 diagonal connects to it. I can enter via one and exit via the second one. And I can now do the same trick again for this triangle because it has 2, actually 3 diagonal edges. So I can go to the next one. But as I'm walking from one triangle to another, this process must terminate at the end. Again, I will never be on a cycle because it's not a simple polygon. Think about it. If I went through a cycle, then I encapsulated a region inside it where all the vertices out there are not triangulated vertices. You can play a bit with topology, think about what is this path that you compressed if this process never terminates. But it's very easy, and trust your intuition here, your process must end in one triangle that you can enter into via a triangulated chord, but you cannot exit, which is the ear. Simple argument just without mentioning the word dual. So we got an ear in every triangulation. Why does it help us? Remember, my goal is to color all the vertices of this polygon. So, and again, every triangle in my coloring would have one vertex from each color. I will not have 2 vertices with the same color in the same triangle. So, can you color with 3 color a triangle? Yeah, you can. Give every vertex another one. Now, what is the induction? Take your polygon and find an ear. Take your polygon and find an ear. It has, that's what we just proved. Remove this ear. Oops. So it has an ear. Remove this ear. Ignore it. Ignore the part W. What do I have when I do W with the 2 exterior walls that are attached to W? I'm getting a polygon that has n-1 many vertices. our argument was that every polygon with n minus 1, you can color with 3 colors in a legal way. That is, for example, I started, when W was counted, I started from a 4 gons. I cut the ear, now I have a 3-gon triangle. I can color it. Now put W back. Claim W will not run into issues. You will be able to find the color for W. Why? Because W has only 2 edges connected to it. Because it's an ear. So whatever is the color of this point green, whatever is the color of this point red, W just takes the remaining color. As opposed to the case of had I tried to add G right here, I'm not sure that I can find a color for G because it has so many neighbors and I need to satisfy all of them. Voila, and we're done. Everybody understand? I moved from 3 gons to now I can color every 4 gons. Now when I convince you that I can do every 4 gons, I can start speaking about 5 gons, cut an ear, getting 4 gons, color it, and then putting the ear back and find a color for the vertex that I just put back. Okay, last thing. You actually need n over 3 many guards. Depending on your polygon, of course, convex polygon, 1 guard is enough. In the homework, I'll ask you to ask if a polygon is actually can be guarded by 1 guard. It's a bit surprising that you can determine it in linear time. That will be a cute question. I'm giving you a simple polygon. Tell me in linear time, expected linear time, if 1 guard is sufficient to guard all of it or not. But what about finding the optimum number of guards? You can use ILP in some way, integer linear programming. The problem itself is NP hard. Many brains thought about approximation of this problem. But there are cases where n over 3 is really the lower bound. Remember, we just proved that it's upper bound. Every simple polygon, you don't need more than n over 3. Here is an example that you need no less than n over 3. This comb that we'll use a lot when we'll talk about Minkowski sums, this comb that has n over 3, or it has n triangles, and I need n guards to guard it. But it has n times 3 many vertices, so I'm not lying. Right? To see this teeth of the comb, I have to have a guard that is somewhere in this region. A guard that would be to the of this side of my hand cannot see into the peak of this teeth. So you must have a guard somewhere here, you must have a guard somewhere here, another guard somewhere here, and so on. So n over 3 is, in the worst case, a tight lower bound. And we are done with this one. I'll skip the algorithm that I don't find very enthusiasm to talk about how to triangulate a simple polygon. We will talk about triangulating sets of points. Okay. Questions about the art gallery theorem? I think that it's really cute and nice, and the proof combines a lot of ideas, this whole guarding part. So the usage of coloring, I think that it's pretty cool. Okay. Okay, I will be ashamed to show you what I wasted my time on today just because I got excited that I now could. You'll see in a second why and why I think that it's such a huge time track. So we're going to speak about combination of Voronoi diagrams and how they are related to good triangulation of sets of points. So first, Voronoi diagrams. you're giving a set of hospitals, set of sites. These are points in this case, but I'll call them sites nevertheless because I'll speak about other types of points, so I want to say. Data points are the sites. These are the hospitals that you see over here. And I want to create the Voronoi diagram of these sites. So what are we doing? What is a Voronoi diagram? It will be a partition of the plane into cells, partition of the plane into cells, such that every 2 points that is in one of the cells, every 2 points that belongs to the same cell, if you ask this point, what is your nearest hospital, it will say it's P4. If you ask what for this point, what is your nearest hospital, it's also P4. Okay. 2 points are in the same cell if and only if the nearest hospital, out of all the hospitals, is the same. They have the same nearest site. Okay? So VD of S, Voronoi diagram of S, is a partition of the plane into, as any other map, it partition into faces, edges, and vertices, intersection of a few edges. But it's not just a map, it has a special property that for every 2 points in the same cell, in the same face, they have the same closest site. Okay? So what's a Voronoi diagram of 2 points? If I just have 2 sites, what's a Voronoi diagram? Yeah, a straight line, which one? It's takes these 2 points, what are the locus of all the points that have exactly the same distance from this side and this side. It's just their perpendicular bisector. Right? Take every point along this line, it has the same distance to this guy, the same distance to this guy. So we already studied something really important for this Voronoi diagram, right? Now you know what are these edges. These edges are, what is this edge? Where does this edge sit on? Every point along this edge, because this one doesn't have a label, every point along this edge has the same distance from P4 and P3, meaning that I'm not using the whole length of the bisector between P4 and P3, but this segment definitely sits on P4 and P3. Every point along it is equal distance from P4 and P3. It's part of the bisector. Every point along this segment is on the bisector of P1 and P4. Okay, so you know what is the edges of the Voronoi diagram. What's special about this vertex? It is so equal distance from 3 points. A equal B, B equals C means A equals C. This vertex is of the same distance of P2, P4, and P1. And the distance to every other point is larger than this distance. Okay, so a segment will be a part of the bisector. So you already have an algorithm for computing the Voronoi diagram. Namely, it's not extremely efficient, but it says construct a bisector between every pair of points and square many lines, right? How many lines for how many pairs do you have, and choose 2. A bit quadratic, and take the intersection of all these points. That would be one algorithm. Here is a better algorithm. I'll pick one of my sites, and I want to know what is the Voronoi cell of it. I'll ask what is the Voronoi cell of this point in the middle. So, and it's important to see where I'm going with this because it will tell us a lot of things about how a cell looks like. So I'll take this point in the middle and I'll compute the bisector of this point and this point, somebody else. And what do I know about this whole face of this point is that it's all on the right side of the bisector. What else do I know about this cell? Take another bisector and take the half plane that the other bisector defines. We know how to compute intersection of half planes, right? It's just a feasible region of linear programming, right? Take the bisector with each and every point and take their intersection. You can do it in n log n. How can you do it in n log n? You can do divide and conquer because the intersection of two convex polygons, if I have one convex polygon and another convex polygon, if each one has n segments, then you're doing line sweep, then you can do the line sweep in linear time and compute the intersection of two convex polygons. I ask you some details about similar idea in homework too. And if you can do it with two polygons, each with in half, then you can now do divide and conquer. That was one algorithm to compute the intersection. You can sort them by slope and then do it in linear time. Details, I ask you in the homework about details. We'll see another algorithm to compute the intersection between them because we will make every half plane and make it into a point somewhere in some dual space and compute the convex half, and that would be exactly what we'll did. So another algorithm is waiting for us. Anyhow, intersection of half planes you can do in n log n. Everybody understands the divide and conquer that I just rushed through? Good. So that's to compute one cell. Now I can do it for each and every cell, and it will be, of course, it will run in n squared log n. Better than the n to the fourth that will be based on computing all the bisectors and computing all the intersection points. That would be very inefficient. Voronoi diagram has lots and lots of nice properties, like here, assuming that I don't have 4 points that are there no 4 sides that are co-circular. What does it mean? I assume that general position will mean that you don't have 3 collinear points on one line. Now, every 3 points define a circle. I'll assume that there is no 4th point on the very same circle. Every 3 points determine a unique circle. Okay, so Voronoi diagram will be a planar graph. Somehow it's not that surprising. What else? Look at the faces of the Voronoi diagram. It's a bit hard to see with the colors. Look at the faces of the Voronoi diagram. Some of them are unbounded, some meaning contains points in infinity, some are enclosed and limited in their own world, bounded and discrete. The one in the middle is the only bounded one here. What can I say about which ones are open to infinity? It's exactly the one on the convex side of my points. Just a cute property. Yeah, the Voronoi diagram will be a planar graph. That's already we said. What can I say about the shape of every face? Is it convex? Prove it. They are absolutely convex. Put 2 points in a face. The segment between them is also in the face. But what's the proof that they are convex? By the way, there are, yeah. Intersection of convex shapes is convex. I just gave you I just told you that every face is the intersection of the correct half planes, the correct sides of the bisectors of it. Right? So every cell is convex. How many faces do I have? Or let's start one step earlier. Are the faces necessarily connected? And all I said is that if I have 2 points, every hospital has a region that is closest to it. Does it have to be connected? Well, yes, because it's convex. Convex shapes are connected. No, connected meaning that if you take a path, there is a path that connects them. Obviously, the segment between them is in the shape, then they are connected. How many faces do I have if I have n hospitals? There will be n. Why? Because I mean, I cannot have, because every site has at most one face, but how do I know that every site has a face at all? Well, but it's very easy to change the distance, and then maybe there are some sites that don't have a point associated with them. If I'll say that every hospital, there is a weighted Voronoi diagram that has, for example, that every point has a fixed cost plus the distance to this point. Okay. It's easy to create other Voronoi diagrams with some hospitals, some sites don't have a representation, but here in the nearest one. Why do I say that that the number of faces is exactly the number of sites? Every hospital, if you're just on the hospital, you're the nearest to this hospital. There is a face that is in this hospital. And so the number of faces is exactly the number of sites. Is a Voronoi diagram connected as a graph? Connected meaning from one point on the boundary of the Voronoi diagram, of an edge of the Voronoi diagram, can I go to every other edge by working on the Voronoi diagram? Almost always yes. Here is an example that no. I have a set of sites and the Voronoi diagram is a set of parallel lines. If I just break this collinearity by just one point, then suddenly it's connected. Now I can get from every point to every other point by just walking along the sides. More property. We say that every cell is convex and each cell contains a unique point. The number of sites is the number of cells. There are no parallel edges, so how many vertices will I get? Order of. Why do I have order n many vertices? Let's try. I have faces that have n edges, almost n edges along them. And if I'll say here I have n edges multiplied by the number of edges, I'll get to n squared. Why do I still argue that this is a very pessimistic bound and I just have linear number of edges? Linear number of edges, linear number of vertices. Euler formula, remember? Number of faces plus number of edges minus number of vertices equals 2 always. So the Voronoi diagram, to be precise, number of vertices is at most 2n. You can think about it as go from every side to the leftmost point and to the rightmost point, and you'll hit a unique vertex in each way, and you are not leaving any vertex unbounded. That's an alternative proof, or just use Euler formula. It will also tell you that you can only have linear number of edges, linear number of vertices. Okay, more properties that a vertex is, every vertex of the Voronoi diagram will be the center of a circle. And I know that I gave you a hard time about it in homework 1, but here I don't distinguish between circle and a disk. I'll use the same term, even though look at a vertex. It is a center of a circle that has what? A vertex is on 3 faces, determined by 3 hospitals. What happened with this disk? It is empty in its interior from every other side because the nearest neighbor of this vertex is either this hospital or this one equidistant, and every other hospital is further away. So it's an empty disk. Right? So, and every edge, what can I say about an edge? It's this look at a point on an edge, a point on the edge. It is also the center of an empty circle that have only 2 points, exactly 2 hospitals on its boundary. A point on the edge of the nearest Voronoi diagram will mean I'm equidistant from this point and this point, but my distance from here to every other hospital is larger. So these are the 2 nearest ones. So this will be an empty circle. Okay. Of course, there are a lot of such empty circles that this edge determines. Okay, now, if I have a set of points how do I construct the Voronoi diagram? You can do it in n log n. Fortune algorithm does it in n log n. But instead, what we are going to describe is not this algorithm directly, but we are going to describe how to build the Delanoy triangulation. And from the Delanoy, it's very easy to get the Voronoi diagram and vice versa. Voronoi diagrams are extremely useful. Don't take my word, Google for it. Quick example, machine learning. I have 2 sets of sample points. Dogs over here, given by weight and height. And cats over here, given by weight and height. I'll give you a query point Q. How do I know if it's a dog or a cat? I look at the nearest animal to Q, or the 3 nearest animal to Q, and ask, are they mostly dogs or are they mostly cats? So it's really important to know, to be able to look at a query point and efficiently determine what is the nearest neighbors. In 2 dimensions, not a big deal. In higher dimensions, the complexity of the Voronoi diagrams is like most things, there is a curse of dimensionality. Most algorithms that have more than fixed number of dimensions have some exponential thing that grows exponentially in the dimension. So what you can do in higher dimension is aim for approximated Voronoi diagram. You can download libraries that up to 20, 30 dimensions work very well. And what do they promise for 20, 30 dimensions? 20, 30 dimensions, meaning that to build the exact Voronoi diagram in 20 dimensions, it will have a complexity of theta of n many sides to the dimension half. So 30 dimensions, 1,000 points to the power of 15, not practical, but it is very practical to build a structure that is almost nearest neighbor. Meaning what? If you have a point Q, a query point, and you want to know what is the nearest hospital, the nearest site, just in higher dimension, weight, height, color, fair, whatever. The nearest neighbor of Q is the nearest point to Q. What I'll get from the approximated Voronoi diagram is some other point P, not necessarily the nearest neighbor. Maybe P will be the nearest neighbor to Q. But even if it's not the nearest neighbor, then I'll make sure that the distance from my query point to the approximated nearest neighbor is only by epsilon many percent larger than the distance to the real nearest neighbor. Make sense? Here are my cats. Here is my query point. Here is the nearest neighbor of Q, this point over here. Possibly you'll get this point as an answer, but if it's not the nearest neighbor, then it's just by a few percent epsilon that you are determining more expensive than the nearest neighbor. Okay, so it's put it in some shelf in your brain to know if you'll ever need nearest neighbors. In higher dimensions, there are also a lot of tricks that uses sensitive locality hashing, a lot of other techniques for approximate nearest neighbors in higher dimensions. And let's start with talking about triangulations and maybe get to Voronoi triangulation. Triangulation of a set of points. We had triangulation of a simple polygon. Now I want to triangulate a set of points. Input a set of points, output triangulation, partition of the world into triangles using chords similar to the polygon. Every chord connects two data points. Every chord connects to data points. You cannot add any more chords, so what you're getting is a set of triangles. And of course, no two chords cross each other. Extremely important, and you see that for the same set of points, there are actually exponentially many types of triangulations. I can triangulate the same set of points in many ways. Really, really important. Your graphics machine wants it, your 3D printer wants meshes, triangulation. Triangles, basically, it's a manifold, it's a surface, it's approximation of the skin, approximation of a smooth creature, and so on. Triangles are like very basic units that we want our graphical device to work on. Okay, why our triangles are so important is you can think about every point as maybe there is some other parameter besides the xy value. I can think about it as possibly the height of this point above the sea level. So it's actually a 3D structure. And what I'll decide about when I'm inside a triangle is I'll assume that here is a height here in these 3 points. So this triangle is actually aligning somehow in 3D. And it's really important how you are doing the triangulation in a reasonable way, and it really influences, because if you are doing linear interpolation, this point is much closer to you, quite higher. These points are all in sea level, and now if I triangulate this triangle using only these three vertices, then every point in this triangle will say I am on sea level value, 0 elevation. Different triangulation for the very same points will tell me something very different for this triangle. So there is not exactly correct and incorrect, but there is a correct answer, which will be Voronoi triangulation. That is like, if you don't know anything about the data, that's probably good. Quick visit into barycentric coordinates. How do I do linear interpolation inside a triangle? There is a very simple formula that all your cell phones and computers know because to do in hardware, actually. That's what your GPU are doing. So think about these 3 vertices and think about a pixel that stands somewhere inside the triangle that these 3 vertices are associated with. So let's think about a segment. A segment between P1 and P2, and I can think about some point Q along this segment. Then I can think about giving some weight W1 into P1 plus some weight W2 into P2. And if I make sure that W1 and W2 are convex combination, what is a convex combination when I talk about weights? It will mean the weights of W1 and W2 must both be positive, and they should be summed to 1. W1 plus W2 equals 1. So if I give weights to these 2 points in this way, usually I'll do it in some less complicated way. I'll just call W1 T, and I'll call W1 1 minus T. And then I'm sure that they sum up to 1, and they are both positive if T is in the 0. And when I'm changing T between 0 and 1, my point Q moves along this segment. You all know it, I'm just reminding. And reinforcing what is a convex combination. What happens inside a triangle, it will be completely analogous. I want to say that if V1, 2, 3 are points that might be in 3 dimensions, might be in 2 dimensions, but the 3 of them refers to a triangle, and I have some point in the middle of the triangle. I can express every point on the middle of the triangle as alpha 1, the weight will be alpha 1 times V1 plus alpha 2 times, it's a point, it has coordinate x, y, z times V2 plus alpha 3 times V3. And alpha 1, alpha 2, alpha 3, these are my weights, should be convex combination, meaning they should be sum up to 1 and should all be positive. Exactly what we had for a segment is now for these 3 weights, alpha 1, alpha 2, alpha 3. And if I'll change all these combination of alpha 1, alpha 2, 3 with these properties, I'll generate every point inside the triangle. Again, if I play with these points, for example, I can put all the weights to be the weight of alpha 1 to be 1 and the other 2 weights will be 0, and then I'll be exactly on the vertex V1. And this is really important because your GPU uses it both to generate, to interpolate the location of pixels in fragments programming, the location of pixels on a triangle, as well as interpolate other properties. Here I played a bit with take colors to the 3 vertices, red, blue, green, and I'll take a point in the middle. And by computing these coefficients of alpha 1, alpha 2, alpha 3, I'll generate the color of this ellipse depending on where this point is. How do I exactly compute these weights? I will connect my point P into the 3 vertices, generating 3 triangles. And I thought to demonstrate it with colors, so here is a blue vertex, and the blue vertex is associated with a blue triangle over here. The triangles that don't touch the blue vertex. The green triangle is a green vertex is associated with a green triangle. Which triangle of the 3 is the one that doesn't touch the green vertex? And the same for the red. So now when you know what are the 3 triangles, I can tell you what are the coordinates. These are the barycentric coordinates of the point P. What are they? Take the triangle, to know what is alpha I, the weight of vertex I, take the area of the triangle that doesn't touch it out of the 3, divide it by the area of the big triangles that they are in, the sum of the 3 individual triangles, and it will give you a fraction of the value between 0 and 1. Right? So if the blue triangle has very small area comparing to the other ones, then my ellipse will be very non-blue. If I'll make this vertex so on this edge, then I don't have blue at all, And then it's just taking us back to the linear interpolation of where I am across this edge, closer to the green or closer to the red, which will just be the ratio between these two triangles. But as you see, here I take my point P very close to the blue vertex, so the blue triangle is huge comparing to the other one, and my ellipse is almost completely blue. To be precise, the RGB color of the ellipse was just the alpha 1, alpha 2, alpha 3. That was exactly the RGB values that you see in this case. So that's how we are doing, how we are using linear interpolation. How do I triangulate a set of points? Here is a not that efficient algorithm. Select a side. Select two sides. Look at the segment between them. Do they intersect any existing segment? If not, take it. That was the first one. Take another segment. Another one. Another one. Another one. Another one. Another one. Oops, that intersects existing segments. So you don't take it. And keep on going. Right? Until you are done, and when you're done, obviously, there is it will be a full triangulation. Another edge that was taken by mistake, and so on. And it must be a triangulation. Why is this n cube? Because there are n square segments and it takes linear time to check. But we are trying to get much better running time. Okay, so here is a much better algorithm, but no guarantees about the quality of the triangulation. You still don't know what do I mean when I say quality of triangulation, but it will be clear soon. So what do? I create the edges of the convex hull. They must be in my triangulation. Take the convex hull of my point, of your point set. And now add a point. Add a point. This point might fall inside the interior of one of your triangles, and then just connect it to the three vertices of this triangle, and move on to the next point. So far, all the points that you have are fully triangulated. If your point is on an edge of the triangulation, then what? It is inside kind of two triangles. I'll connect it to this triangle, and this triangle, that's all I need. And moving on. So either adding two edges or adding three edges, depending on the context. And this starts to be a reasonable algorithm and will lead to actually a reasonable triangulation, but with a bit further assumptions. How many triangles do I have in the triangulation? So please stay awake. It's a really cool proof. Really, really cool proof. I want to ask how many many triangles I generate in the triangulation if I have n points. And the answer is that if you just tell me what's the number of points that you have, I still don't know how many triangles. You need to tell me two parameters: how many points and how many of them are on the convex hull. Again, I need to know how many points you have and how many points you have on the convex hull. So, question. Here is a polygon with 1, 2, 3, 4, 5, 6 many vertices. Please tell me what is the sum of all the angles that I just showed you. The sum of all these angles. Sorry? Maybe. No. I think yes, no, maybe yes. Maybe. For some value of 6, doesn't have to be 6. For n, go. How do I compute the sum of all these angles? So here is a quick trick. It's convex. Take one of the vertices and take its triangulation by connecting it to every other edge. How many triangles do I have? I have n minus 2 triangles. So far, sum up the sum of all these angles. So it's n minus 2 triangles times 180. Okay, that's how I compute how many, the sum of all the angles. Now, here is a set of points that have also points not on the convex hull. And I'll show you two ways to sum up all the angles of all the triangles in the triangulation. Again, I want to sum up the angles of all the triangles in the triangulation. So one way to sum up these angles will be, in a convex h-gon, the sum of angles is h minus 2 because it's a number of triangles, like in this case, h minus 2, each one contributes 180 degrees. That was the sum of this guy, this guy, this guy, this guy, this guy, this guy, the exterior ones. So the h here, well, I don't call it n, because n is the total number of points. H of them are on the convex hull. And some 2 in this case are in the interior. So far I summed up the exterior angles. No, not the exterior, but the one on the convex hull. And now, what is the contribution of an interior vertex? Sum of all its angles sum up to 360. So I have h minus 2 times 180 for the outer one. And how many interior points do I have? N, which I started, minus h, number on the convex hull, times 360, each one of these guys contributes. That was one way to sum up all these angles. Here is another way to sum up all these angles. If you have T triangles, each contributes 3 angles that sums up to 180. So if somebody will tell me what is T, the number of triangles, and I'll multiply it by 180, I should get the same answer that I got earlier. So what do we get? H minus 2 times 180, one from on the exterior walls, plus 2 times 180, is 360, times n minus h, equals to T, our unknown number of triangles, times 180, which every triangle contributes. 180 vanishes, and you got the formula that tells you how many triangles you have. In particular, you see that the number of triangles in every triangulation will be the same, for the same set of points. Let's start handle the issue of quality. Kind of subjective issue, what is exactly this quality? But as a rule of thumb, we want round and chubby triangles. They are behaving much better. Why? Because very skinny triangle in this aspect, think this point should interpolate its value based on some, you want to guesstimate what is the color or the height at this point. And if in the approximation, you have some points that are A, very far away, and B, you're just near a very other skinny triangle which can change dramatically, somehow it doesn't smell good. For many applications, we would like to say triangles that have all their angles are big are good triangulation. Triangles that have very thin triangles are, of course, application dependent, but as a rule are less preferable. Here is another way to think about it. I measure the elevation above the sea level in this quadrilateral, and it turns out that this is 100 feet, this is 100 feet above sea level, and this is 0 and 0. And I want to make this picture even a bit more extreme. Let's say that this point and this point are both 0 elevation, and here you are very high, and here you are very high. What is the geographic feature that you think that it represents? We cannot know, I need more data points, but we have like 2 guesses. I'll ask you about this point. What do you think your elevation here? There are 2 options. This is a tall mountain. This is a tall mountain. These are in the valley, in the sea level height. Possibly, this valley continues over here to a very short distance, which I think makes sense. Or possibly, there is a very long ridge, which is also extremely sharp, because this is, if I need to approximate, then every point along the segment should be 1,000 and 1,000, while it's very steep change to a very nearby point. So without any data, we like it less. So now we can associate a vector that will measure the quality of the triangulation. Well, again, take quality in quotes. For most applications, it's correct. What will be this vector? I look at all the triangles in my triangulation, and I'll ask what is the nearest edge, what is the smallest edge that any triangle generates? Alpha 1 will be the smallest edge of any one of these triangles. Alpha 2 is the second smallest angle. What do I mean? If two triangulations that I have, and in one of them, the smallest angle is larger than the smallest angle in the other ones, that is, one of them has a really tiny angle, while the other one has all the angles much larger, I'll prefer the one that the smallest angle is larger. What happens if I have two triangulations that have the same smallest angle? Then I'm looking at the second smallest and ask which one is smaller. Okay? And if both triangulations have the same first and second, then I'm looking at the third one. Same way that you are sorting phone book, right? If two names start with the same letter, then the one that has the smaller second letter will appear earlier. Okay, so what can we say about the Voronoi triangulation? What do I say? Why do I say that the Voronoi is a 42 answer from Hitchhiker Guide? That it's like the universal answer? Well, because it has the best. I mean, if my point set sucks, if my point sets has this point and a lot of these points, then no matter what I do, somebody needs to give up. I will have small angles. But if I have some freedom about the triangulation, the Voronoi triangulation will be the best triangulation that I can generate in terms of this vector. It will give me the best vector of angles out of any other triangulation of this particular point set. Okay. And now we start to put these things together. A lot of material today. Now we start to put these things together. So what is a Voronoi triangulation? We talked earlier today about dual graph. Remember, dual graph, I have a set of, I start from a map, and I connect, I put a point inside every face, and I connect this point if the faces touch each other. Here I have hospitals. A, B, C, D, E are my 5 hospitals. I can create a Voronoi diagram. The Voronoi diagram that we just discussed. In the Voronoi diagram is a map. So I can look at the dual graph. What will be the dual graph? I'll take every 2 faces that shares an edge, that is 2 hospitals that share an edge interface, and connect them by a segment. B and C are neighbors. B and C are neighbors. Why do I say that they are neighbors? Because they share an edge. I connect them by a segment. Now, the segments might intersect another Voronoi face. That's okay. It's not an issue. As long as these 2 faces are neighbors, I connect them by a segment. And the same I'll do for all of it. E and C are not neighbors. E and C are not neighbors, so there is no edge between them. There is no edge directly. D is somehow in the middle, but there is no edge between E and D. Okay, so I created the dual, but I created the dual in a very specific way. I'm not just picking arbitrary point in the face, I pick the site of this face. I'm using the Voronoi diagram and compute its dual. Connects every 2 sites that are neighboring each other. What will you get? We'll have to prove it, but we'll get a triangulation. And this will be the Voronoi triangulation that give us the best angles, etc., etc. Okay, so in particular, the it will have the property that, how is this related to the Voronoi diagram? Well, we will see that if we look at every triangle in the triangulation that I generate, and I look at the circle through the 3 points of this triangle, the center of this circle is what? It's the Voronoi vertex that is exactly in the intersection of these 3 points. We'll discuss this much more if you don't follow me. Look at every triangle of the triangulation, look at the circle that it defines, it will be empty of any other data points. The same goes for this vertex, its circle will be empty. These 3 points, their circle will be empty of any other data points because of properties of the Voronoi diagram. And what will be so desired in having empty circles is what connects it, and that's what I wasted my time today, is a Thiel's theorem. I discovered that you can do GIFs with GeoGebra. So if you're looking at what does Thiel's theorems tells us? Remember, our desire is to get big edges of all our triangles. What do I see in Thiel's theorems? So I see a few points. Can I freeze it? So I see here, I look at one particular segment, A, B, and I think about a circle that goes through A and D. Okay, I created one particular circle that goes through A and D. And now I'm standing on this circle, and I watch. I see A, I see D, and I look at the angle that I generate. At which angle do I see this edge of AD? And it happens to be 58. And then I'm moving a bit on this very same circle, and I do the same experiment. Look at AD, at which angle do you see them? Surprise, surprise, 58 degrees, the same 58 that appeared right here. Okay, and the same will happen as long as I'm moving along this circle. Any point along this circle, as long as I don't change it, will watch this segment in the same angle. But what happens if I make this angle a bit larger? Then my points getting further away, and this angle that is still the same in both will become smaller and smaller. So in general, if I have a circle that contains the data points, it will be a bad sign, because it will mean try to get somehow a smaller circle. It will make the angles of this triangulation that I'll talk a bit larger. Try to get closer to the edges, and it will make your edges larger. So I need to show you, otherwise I'll feel very bad. I need to show you about edge flip. Look at a quadrilateral. A, B, C, D. And I'll assume that in this quadrilateral A, B, C, D, it's convex, because you can have a non-convex quadrilateral. And I'll assume that it's not cos-circular. So you have, and in this quadrilateral, there are two diagonals, either AC or BD. And I want to say that one of them is legal and one is illegal. One is good, one is bad. Which one is good and which one is bad? I have to do it. It's for me. So I want to say, if your circle that goes through A and B, if it contains the other vertex, then it's a bad diagonal. Again, if the circle that goes through a diagonal contains one of the endpoints, then I can move it so it touches the other endpoints, but always one of these two other vertices are inside the circle. It's not an empty circle. What I try to show in this animation is that if the circle that goes through A, C, and A contains B, then the circle that goes through A, B, and C contains D, and vice versa. That is, if the circle A, D, C contains B, then at the same point, the circle that goes through the same vertex, and the other side contains the opposite vertex. And then, at the very same time, if the circle through three of them does not contain the fourth, then the circle through this edge, and this edge does not contain the fourth. So now I can define what is legal, what is illegal. Look at the two diagonals. If your circle through three of them contains the fourth one, then this edge is illegal. What do we do with illegal edges? We flip them. Every diagonal that you'll see where this triangle contains an edge, flip it, it will make all the angles that sit on these edges larger. It will make all four edges that are defined here will be larger. So out of the two diagonals, one is always legal, one is illegal. And our algorithm will be based on adding some points, and once you're adding a point, if it's not a Delanoy triangulation, or the triangles are empty circles, then start flipping edges. Hopefully, was the time. Thank you. Okay.
I said you didn't know about it, and you just said you had it covered, but I just wanted to make sure the grade scale wasn't updated.
I thought I updated it. I thought that I changed it. You said, I think that I didn't get to the next page. Was it a case that I said it's not an algorithm?
It was the what, sorry?
A case that I said it's not an algorithm. If that was,
Let me-
if we are talking about the same thing.
I have grade scale.
Sure.